in here. How much of you all have, well, I'm pretty much sure, I shouldn't ask this question. Everyone here has seen a periodic table. The assumption here is that everyone has seen this, they have a general idea about the periodic table. And of course, we'll be discussing little things about it as we go along. The periodic table is just a table of all the elements found on Earth. I know it looks intimidating, but the truth is, in school, your teacher tells you you only have to learn off how much of the periodic table by heart. Do you have to learn all 200 or only the first, 20? I'm sure everyone's teacher has told them that, and I agree with that, okay? So anyway, let's move on from this scary looking table, and let's do some quick basics. In your periodic table, right, here's a little snapshot of some of the elements like hydrogen, lithium, beryllium. On your periodic table, there's usually a small number. I'm gonna choose lithium here, and there's usually a larger number. Now, on your periodic table, for some strange reason, the smaller number does be on top, and the larger number does be underneath. However, if you were to write lithium outside of your periodic table, right, the larger number goes on top and the smaller number goes underneath. How much of you all have realized that inside the periodic table, the smaller number goes on top, but the larger number goes underneath? But when you write it by itself outside of the periodic table, you have to write it reverse. And how much of you all have actually noticed that? This used to confuse me in school. Nobody never really explained why, right? And up to now, I don't know why, right? Up to now, I can't get an explanation for it. So let's talk about the symbol when it's outside the periodic table. And that is what this note is about. So here we're going to use a general example, X. Remember, the larger number will go on top, and it's usually represented by the letter A. It stands for the mass number, and the smaller number, which is usually represented by the letter Z, is called your atomic number. Your atomic number tells you how much protons, and I have a little symbol here. Remember, protons are positive. And the top number, the large number, is the amount of protons plus neutrons. So that's why the top number is large. It's the amount of protons plus the amount of neutrons. Do you all realize that there's two things missing from this? How come there is no number that tells you how much neutrons it has alone? I mean, it tells you how much protons it has. It tells you how much protons and neutrons it have together. But why isn't there a separate number to tell you how much neutrons it has? The reason is, to figure out how much neutrons it has, you just have to minus the big and small number. How much of you all knew this from school already? Right now, remember the assumption here is that everyone at least did a little bit of chemistry before, right? So you have a little bit of knowledge about the protons. So come guys, everyone send me an answer. Get involved in class on the chat, right? On the chat, okay? Right. Great. So to figure out the amount of neutrons, you just have to minus both numbers, the large number and the small number. So quickly, lithium has how much neutrons? We know it has 3 protons, because the smaller number underneath is the amount of positive particles called protons. So how much neutrons does it have? The amount of neutrons in lithium would be 4. 7 minus 3 is 4. And don't worry, I'm going to constantly be harassing you about remembering that. To figure out the amount of neutrons, you just minus the big and small number. But something else is missing in this information here, right? You all realize that the examiner, but not the examiner, on the screen, they're so happy to tell you how much protons it has. How come they didn't tell you how much electrons it has? The reason is because of this note. Protons and electrons are supposed, keyword, supposed to be equal. Your protons are your positive charge, your electrons are your negative charge. And it's supposed to be what? Equal. So lithium has 3 protons, so 3 positive charge. So by default, it will also have 3 negative charge. And of course, the charges are supposed to cancel out each other normally. So 3 positive and 3 negative, when they clash, they give you a charge of how much? 0, as simple as that. So here's what I need for everyone to do, all right? To keep it simple, you're only taking down this. I'm going to circle exactly what I want you to take down, right? And these 2 things, not circle, but highlight what I want you to take down. This is everything that I just discussed. And don't worry, for those who are not too familiar with protons, electrons, and how to calculate the neutrons, like I said, I'm going to constantly be saying it over and over. Take down the notes. Let me know when you are finished. All right. So let's just quickly draw some atoms and just refresh your memory on some of the work you may have done in Form 2, whether it was chemistry or it was just simply integrated science at that point in time. So here we have an element. Anybody wants to tell me what's the name of this element? It's an easy question, but just to get everyone talking. What is Na? All right. This would be sodium, right? Sodium is actually a metal, right? It's not a very hard metal like iron or like copper, but sodium is a type of metal, right? So you will notice that it's written outside of the periodic table. It have what? A big number on top and a small number underneath. All right, so let's do some quick calculations here. The small number is the amount of protons. So, and the protons have what? A positive charge. Remember, protons and electrons are normally equal. So that means if it have 11 protons, it also has how much electrons? It also has 11 electrons, right? Protons and electrons are equal. Anybody wants to tell me how much neutrons it has? Remember, neutrons, you have to minus the big and the small number. So let me write it here. 23 minus 11, right? 23 minus 11, for some reason, I can't do that in my head, so I'm going to steal your answers, right? Neutrons equal 12, okay? Simple stuff, right? Oh, by the way, what's the charge on a neutron? Is a neutron positive, negative, or no charge? Right, the neutron has no charge. Now, in case you all didn't remember, protons and neutrons are at the center of the atom. You call that the nucleus of the atom. So it has 11 protons. So I'm not going to draw 11 protons. So I'm just going to put positive 11, meaning that it have 11 protons. And you're allowed to do that in the exam. If something has 11 protons, you don't have to draw 11 circles and name each one a proton. You can just put 11 plus. The examiner will know that you mean what? 11 protons. What am I going to put in the blue circle? What number am I going to put in the blue circle? It's going to be 12, correct. You guys have it correct, because this 12 represents the amount of neutrons, and neutrons have no charge. So I'm not going to put a positive sign or a negative sign. In case you all forgot, electrons revolve around the nucleus. So the electrons will go on the shells. For CSEC purposes, to represent electrons, you can either use a dot, like a shaded dot like this, or you could use an X. That's usually the general two symbols accepted to represent what? Electrons. Sometimes I'm going to use the dot. Sometimes I'm going to use the X. Today, I'm going to use the dot. How about that? I feel like using the dot today. The first, remember, it's supposed to have 11 electrons as well. Do you all remember how much the first shell can hold of an atom? The first shell, not 4, it can hold how much? Up to 2, correct. The first shell can only hold 2 electrons. And after the first one, the rest of them can hold how much? 8, right? So you all remember. So for the first shell to be filled, once it has 2, it is filled. So we have 2 so far. The next shell can hold up to 8. 1, 2, 3, 4, 5, 6, 7, 8. How much do we have so far? We have, on the board, how much I have so far? 10. Remember, we need 11 because protons and electrons are supposed to be equal. Now, the first shell is filled. The second shell is filled. It can only hold 8. So only 1 goes on the last shell. Right? Great. Remember, this is just revision from Form 2, right? It's just basic revision, but it's super important. And questions like this actually come for CXC. So that is real good news. Tell me something. Is this atom neutral? Is the overall charge 0? Is this a neutral atom? Yeah, so a lot of people are saying the answer is yes. Okay, this is a neutral atom. Let me explain why. How much protons does it have? And it have 11 protons. And how much electrons does it have? 11 electrons. And 11 positive will cancel out 11 negative. They are perfectly equal. So the positive is not larger than the negative. There's no winner in this case. Okay? Take down everything on the screen. Right? Believe it or not, if this comes in the exam, this is a nice 2 marks, easy 2 marks in a CXC exam. Oh, no problem, Josiah. Thanks for letting me know. For those who worried about that, you might not have gotten all the notes, or you reach late to class, the class is going to be fully recorded, uploaded, and you can always review, to fill in what you missed. Okay, so we have a little cutscene here today, right? For those who came to class late, you may not know what's going on. So remember, you all chose a character at the beginning of the class, right? So apparently you are an adventurer and you ride for a couple of miles when a ghost, a kind of spirit appears, right? And here's what's going to happen now, right? This is the outcome. For people who chose Asuka, because of her fighting skills, you add 1 to your strength. Death, add 2 to your strength. Sorry, people with Muka, you have to -2. Remember, everyone started with a strength of 2. And Aka, -1. Everyone update their score sheets. So Asuka's add 1, so you have 11 now. For strength, this is for strength, magic not involved. Death, add 2. Muka, -2, so you're on 8, and Aka, -1. At the end of class, we'll see who has the most strength, the most magic, and the most items. All right, so let's move on. You think you all could draw this one for me? This is carbon from the periodic table. I want you to draw the atomic structure for carbon. Right? I know you're not going to be able to send the answer on Zoom as is our picture. But if you want to describe it, like after you draw it, you can say, hey, it had so much electrons, so much protons, and so much neutrons. Good luck. So remember, when it's written outside the periodic table, the small number is usually the amount of protons. Protons have your positive charge, and of course, protons is supposed to be equal to what? Electrons, which have a minus, well, a negative charge. The amount of neutrons is the big number minus the small number. Now, it just so happened 12 minus 6 will give us 6. 12 minus 6. So it has 6 what? Neutrons as well. So how much protons does it have? 6 protons. It has 6 neutrons, and it should also have 6 electrons, right? So apparently in this question, everything is 6. So I'm going to use the X's now. I don't always have to use the dots. You can choose whatever you want. So you have 2 electrons. The first shell can only hold 2. So once that's filled, the rest will spill over to the next shell. And we have 4 more. 1, 2, 3, and 4. How much of y'all had something like that? You can put them in pairs, and you don't have to space them out like this. You can put it in pairs, like 2 here, 2 here. Well, once they had 4 on the outer shell. But usually when you have 4 on the outer shell, in most textbooks, they just space it out evenly to make it look cooler, I guess. And is this a neutral atom? Is it fair to say that this particular one is neutral? I would say yes also, because it had 6 positive, 6 protons, and 6 electrons. Positive 6 will cancel out negative 6, making the overall charge 0. Take a 20 seconds, take down the answer if you got it wrong. Right, so easy stuff so far. Let's go, guys, let's go. All right, so what about this thing called ions, right? How much people have come across something called ions, not iron, not iron, like the metal iron, I-R-O-N. I find a lot of people mix up the word ion with I-R-O-N. And ion, right, is when an atom is not balanced, like it's not balanced at all. For example, let's look at this picture here. All right. Is this particular atom right now neutral? Is it neutral? See if you can figure out which one is the protons, which one is the neutrons, and which one is the electrons. It shouldn't be too hard to figure it out. The white diagram, is that neutral? The answer is, I think the answer is yes, because look at it. It has 3 positive charge. The red one is positive, so it has 3 positive and 3 negative. The electrons are always revolving around the nucleus. So it has 3 negative. So when you work this out, right, the overall charge is going to be what? 0, because the 3 positive cancel out the 3 negative. Fine, that is not an ion. How about this now? Let's say that one of the electrons gets angry. He has an argument with the atom. Let's say it's this guy here. And he says, I am leaving you all. I don't like you all anymore. And he just goes away, right? It doesn't matter where he goes. He just leaves. Is this a neutral atom now? The answer is no, because let me explain why. It still has 3 positive, 3 protons, but it only has what? 2 electrons. Who will win this fight? Will the positive win the fight, or will the negative win the fight? I just basically, well, the one with more will win the fight. Because it has 3 positive and 2 negative, the overall charge will be what? Positive 1. But you can do the maths, right? 3 3 minus 2 is positive 1. You all notice that it is not neutral. Again, the overall charge is positive, and not just positive, positive 1. Now, if it even worse, let's say, if it were to lose another electron, you realize the more electrons it loses, the more positive it will become. So whenever you have an atom and it is not neutral, like one of the charges outweigh the other charges, you call it an ion. But here's the thing. Anytime the overall charge is positive, you call it a cation. Cations are positive. There are 2 different types of ions. One is a cation and one is called an anion. Let me show you what an anion is. Right now, in this atom here, is this atom neutral? Look at it. Is that neutral? Yes or no? This one looking neutral, right? Now, in case you didn't realize, the P stands for protons and the N stands for neutrons, right? Different textbooks will, see it slightly different ways. Now, look how much electrons it has. 1, 2, 3, 4, 5, 6, 7. So right now it has 7 positive and 7 negative, making the overall charge 0. But remember in the first example, it lost electrons. Suppose now it wanted to gain an electron. So an electron was just wandering about, and he decided to join the party now. So he said, hey, can I hang out with you guys? Look at what happens here now. It still has 7 protons, but now it have what? 8 electrons. What's the overall charge here now? Who is going to win? Who is going to win the fight here now? Any negative? The overall charge will be negative 1. Okay? Whenever the overall charge is negative, it's called an anion. Anions have an overall negative charge. Cations have an overall positive charge, right? And I know some of you all who did electrolysis in school probably asking what's the difference between a cation and a cathode, or an anion and an anode. When we're doing electrolysis, we will get to that question. It's not something simple to explain, but I will eventually reach the difference between what is a cation and an cathode and what is an anion and an anode, right? So here's what I need for everyone to do. Take down the definition of what an ion is. An ion is when there's an imbalance between the positive and negative, like the positive is not equal to the negative. But you have to keep in mind there are 2 types of ions. Cations, where the overall charge is positive, or where the overall charge is negative. And it has to do with either electrons leaving or electrons joining the party. Okay. Let me know when you're finished and you're ready to. All right. So we have a little cut scene here. All right. Next on your adventure, apparently if you put it tonight, so you come out to the forest and you see an orange glowing light, and then suddenly an evil spirit appears. Let's see how your stats update. All right, guys. So here's what. Asuka's -2 from your strength, right? Anytime you see a circle above the character, that's your strength. Let's add 4. Add 9, add 2, and Arthur's -2. Update your stats, guys. Update your stats. Also, there's a special bonus. all the asukas and all the akas, only the two of them, add 2 to your magic. You all get a bonus. So asukas and akas add 2 to your magic, right? No one else is getting anything with regards to magic, right? You all updated your stats there, guys, on your sheet of paper. All right, let's move on. Right, if you missed the beginning of class, you're gonna be real lost with the storyline, right? So for those who didn't come in at the beginning of class, just go with the flow. All right. Yeah, the numbers at the top. Let me just clear it up here quickly, guys. The numbers at the top are always strength. At the top of the character is always strength. Always strength. Okay, guys, so let's talk about the different parts of the periodic table. Let me hear how much you all know from school. When it comes to the different parts of the periodic table, I will start you off with one section of the periodic table. And then I have something called the metals section, the non-metals section, and the metalloids section. How much of you all remember that from school? The reason is, right, it color-coded here. Everything in pink are all the metals on the periodic table. Everything that is kind of light bluish is what? Non-metals. And then it have these things called metalloids. Metalloids are, how you say, are elements that are not quite metals, and they are not quite non-metals. They are kind of in between, like they're partly metal and partly non-metal. You don't have to draw this periodic table. Okay. Anybody notice something funny about hydrogen? Does hydrogen look out of place? Is hydrogen a metal or a non-metal? You all notice that every single non-metal is to the right of this line here, right? What about hydrogen? Why is hydrogen the only non-metal that's clearly in the metal region? Anybody has any theories on that? Why is hydrogen so out of place? Let me hear what you think on it. Hydrogen, we know it's a non-metal. Well, I think we established that already. But here's what, he behaves like a metal. Not in all cases, but in a lot of cases, he behaves like a metal. Now, I know some of you all are probably wondering, what do metals behave like? Like, why do we classify something as a metal? And the reason is, right, metals, when they're involved in chemical reactions, they behave a certain way. Their electrons behave in a certain manner. And don't worry, I'm gonna have plenty examples showing you how metals behave when they are involved in a chemical reaction. Hydrogen, even though he is a non-metal, his behavior is very, very similar to a metal in a lot of cases. That is why a lot of periodic tables put hydrogen in the metal region. Everybody think they're okay so far with that explanation, that hydrogen thinks he's a metal. He's not real metal. He's just somebody who thinks he's a metal, and he starts behaving like a metal. And I'm going to show you that later down in class. Okay, great. Now, it have different groups over here, right? So let's go through the different groups. Groups go vertical, like this over here is group 1, this over here is what? Group 2, You don't really count the middle, right? You see this part of the periodic table, up to here, you don't really, for CXC purposes, you don't care about it. So you have 1, 2, 3, 4, 5, 6, 7, 8 groups. Groups are vertical, are things going downwards. So for CXC purposes, there are 8 groups that we consider, okay, that we consider for the syllabus. The first group, not counting hydrogen. Remember, hydrogen is not really a real metal. Anybody remembers the name given to group 1, excluding hydrogen? What's the name given to all the metals found in group 1? Let's see how much you can remember from school. One person have it, right? Group 1 metals are called, and I kind of highlighted, are called the alkali metals. Group 2, things like beryllium, magnesium, calcium go down. You call that the alkaline earth metals. So group 2 is called the alkaline earth metals. Group 1 metals are called alkali metals. It's very easy to mix up because both of them start with E, right? In between here, you see all of these metals that I had scraped off. These metals here are called your transition metals. That's the official name for all the elements in that area. Group 7, remember this is group 7 here. Here was 1, 2, 3, 4, 5, 6. Group 7 is called your halogens. And group 8, which is your last group, they are called the noble gases. They have official names. You all notice that group 3, group 4, group 5, and group 6 don't have official cool names. How come group 1 gets a cool name, group 2 gets a cool name, 7 and 8 get cool names, but 3, 4, and 5 don't get cool names? That's just how life is. I don't have a good explanation for it, all right? So here's what I need for you all to do. And remember, groups go downwards. Make a note. Group 1, make a note like this. Group 1, put alkali metals. And you can do the same thing for group 2. Group 2, write alkaline earth metals. Group 7 is the halogens, and group 8 is the noble gases. It's just a very simple note I'm asking you to make. Everyone okay with making that note? Group 1 is alkaline metals. Group 2 is alkaline earth metals. 7, which is of very special interest in chemistry, is called your halogens. Your halogens are fluorine, chlorine, and those guys. All right. So let's answer this question now. What's so important about naming it group 1, group 2, all the way to group 8? That's the thing I was telling you about just now. Remember at the beginning of class, we were drawing atoms, like you were drawing how much protons, neutrons, and then how much shells. Let's look at this. Sodium, right? I know it's kind of hard to see the periodic table here. It was kind of hard to get everything to fit on the screen, right? Sodium, what group is sodium in? What group is sodium in? You all notice that he is in group what? 1. It just so happens that if you were to draw sodium, it would look like this. Now, I didn't draw the amount of protons and neutrons. I just drew the amount of electrons. So the first shell has 2. If you see it here, the first shell has 2. The next shell has 8. And the last shell only has what? 1. Usually, when it comes to electrons, to atoms, and understanding chemical reactions, we usually just care about what's going on the last shell. So the last shell only has one electron. Like if you were to take your time and draw out sodium, you would only end up with one electron on the last shell. The electrons on the last shell are called valence electrons. And it's no coincidence. Sodium is in group 1 because when you draw it, it would have one valence electron, one electron on its outer shell. Sodium, the K here, sodium, K is for potassium. If you were to draw potassium, when you are finished drawing it, it would only have how much electrons on its last shell? One. It would have one valence electron. Let's look at calcium. Calcium is in which group? 2. When you draw calcium, you all notice how much electrons it have on its last shell? It only has how much? 2. And that is why you put calcium in group 2. Everybody in group 2, when you draw it, you will get 2 valence electrons, 2 electrons on its last shell. Let's look at chlorine. Chlorine is in which group? This is 1, 2, 3, 4, 5, 6, 7. Chlorine is in which group? 7. Look how much outer electrons it has in its last shell. 1, 2, 3, 4, 5, 6, and 7. That is why chlorine is placed in group 7, because everybody in group 7 will have 7 outer electrons. Neon is in group what? Neon is in group what? 8. So guess what? How much outer electrons you would have? 1, 2, 3, 4, 5, 6, 7, and 8. There's only one exception to the rule, and that's helium. Helium, when you draw it, even though he's in group 8, when you draw it, he only has 2 outer electrons. Helium is the exception to the rule. He is the only person in group 8 that only has 2 outer electrons. Everybody else would have what? 8 electrons. So, to summarize, the groups indicate the amount of valence electrons. The exception is who? Helium. All right? And I know I have carbon here, but carbon has how much outer electrons? 4. So you notice carbon is in group what? 4, and rightfully so. Despite this very, very complex looking slide, I only needed to take down this note here. This is the only thing I needed to take down. Everyone clear so far? Things are put in vertical groups based on how much outer electrons it has. No other reason, except for helium. He's the exception. I know I probably said it, right? You call this shells, right? So sodium has how much shells? 1, 2, 3 shells. Calcium has how much shells? 1, 2, 3, and 4. Right? So the amount of orbits, they just call it shells. So like calcium has 4 shells. Helium only has 1 shell. Neon has how much shells? 1, 2 shells. The shells hold the electrons. All right, so that's not so. All right, so the reason I'm talking about shells, because I think the next slide is going to be about shells. Right, so just now we did groups. Groups go up and down. Groups are vertical. Periods are different. Periods are horizontal. They go from left to right. Right, so let me just explain this here. So periods go from left to right. This is the first period. This is the second period. This is what? the third period, okay, and so forth, right? The periods indicate how much shells the atom will have. For example, sodium, you all notice something, right? Sodium, chlorine, and argon, all of them are in the same period. They are in period what? 3. So when you draw out the atoms, you will realize all of them, even though they might have different amount of electrons, all of them will have the same amount of what? Shells. So everybody in period 3 would have the same amount of shells. They would have 3 shells. Everybody in period 2, that's lithium, beryllium, boron, carbon, even though they have different amounts of electrons and different amount of valence electrons, they would have the same amount of what? Shells, right? Right, it's a very short note. It's that small note you're taking there in the corner. All right, so we have a little cut scene here, right? So apparently after a good night's rest, you feel the sun rays on your head and you hear a huge growl. Oh, this scary looking monster is coming towards you guys here. So you get into a fight with what's called this? A minotaur, right? And of course, you're battling minotaur and whatnot. Let's see the outcome of this battle. Asuka, everyone who chose Asuka, add 40 as strength. Remember, the circles on top represent how much strength you gain or lose. Det, add 1. Muka, -2. And Aka, -1. But there's a very special bonus here. Everyone who chose Muka or Aka, you just got a Minotaur's sword. So write that in your items box. Spell it out, and it's going to be very important. This is one of one types of swords you're going to acquire. So write Minotaur's sword in the item list. Anybody want to tell me how much strength you have so far? I just want to know who have the highest strength so far. Not magic, just strength. And let me know your character, because remember, if you send your score, I want to know which character you have, right? All right. I think some of you are having some adding problems. All right. So let's talk a little bit about isotopes now, right? Isotopes are like different versions of the same element. And let's take one of the easiest ones here, oxygen. So let's look for oxygen here in the periodic table. Where's oxygen? Anybody wants to tell me which group? Hear the word I'm asking for. Which group is oxygen in? Group. I want to see if you all mix up group and period. What group is oxygen in? It's supposed to be 6. Look at it. 1, 2, 3, 4, 5, 6, right? Let's put in the other 2 here. So oxygen is in group 6. So that means, right? I know it's kind of hard to see the numbers here, right? It's supposed to have 6 outer electrons. I have it here, right? The oxygen that you see in your periodic table, there are many different versions of oxygen, but your periodic table only displays one of the many types of oxygens out there. And it only displays the most popular type of oxygen. So because oxygen is in group 6, let's look at the structure. It has 1, 2, 3, sorry, the outer shell has how much? 1, 2, 3, 4, 5, 6 electrons. And it's supposed to have 6 what? Outer electrons. Now its normal oxygen also has 8 protons and 8 neutrons. Now, here's the thing. What determines the name of an element is the amount of protons. That's very, very important. The amount of protons determines the name of the element. Now, here's the thing. There's a different version of oxygen. And look at the slight difference. This new version of oxygen still has 8 protons. Is it okay to still call it oxygen? Because it's a rhetorical question. The answer is yes, right? Because both of these oxygens have the same amount of protons, he is also oxygen. But what is the difference? The only difference is this time he has how much neutrons? He has 9 neutrons. And then there's another type of oxygen. It still has 8 protons, but this time it has 10 what? Neutrons. What's the only thing that is changing between these different types of oxygen? The only thing that is changing is the amount of neutrons. So you call these isotopes. Isotopes are different versions of the same element. And the only difference between them is the amount of neutrons. The amount of protons is the same. The amount of electrons is the same. The only thing that is different is neutrons. Now, the first one, because it has 8 protons and 8 neutrons, when you add it up, you get 16. So his name is but let's call him oxygen 16, because when you add up the amount of protons and neutrons, you get what? 16. I know it's kind of hard to see, but that's supposed to be a 16 here. This one here, you call it oxygen 17, because it has 8 and 9. When you add 8 and 9, you get 17. And take a very good guess. The other one would be 18, because 8 plus 10 is 18. So that is all an isotope is. It's just a different version of the same element, except it has a different amount of neutrons, right? And most periodic tables only display the most popular one. Like on Earth, the most popular type of oxygen is oxygen 16, the one with 8 protons and 8 neutrons. Take down the notes, right? You don't really have to draw the diagrams. It is the note is what you really want to take down. Things like isotopes and things, I'm going to be saying it over and over. Like almost every class, I'm going to be forced to talk about protons, electrons, isotopes, periods, groups. Let me know when you guys are finished. Yeah, right? The wizard is saying that the amount of protons determines the position in the periodic table. Because oxygen, notice all the oxygen has 8 protons. You notice he's number 8. Look at it. We count like this in a periodic table. He's the first item, second item, third item, fourth, fifth, sixth, seventh, eighth. Right? So the amount of protons determines the position in the periodic table. All right, guys, so I think I'm ready to move on there. Let's go. All right. How much of y'all came across this now? Allotropes. We just did isotopes. Isotopes are basically the same atoms with different amount of neutrons. Don't worry, allotropes are going to be super, super easy. How much of you, well, you all know this thing called carbon. Remember we saw carbon in the periodic table just now? Well, where's carbon? Carbon is somewhere here. Carbon is number 6 in your periodic table, right? Pure carbon, like if you were to go in the ground and dig out carbon from the ground, what color is carbon usually? Anybody knows what color carbon is? Carbon is supposed to be black, right? Like it's a black substance, okay? Now, the most popular example in CXC is carbon. And allotrope, right? All of these dots here that you see here is supposed to be carbon. Like all of these dots are supposed to be one atom of carbon. How to say this, right? Do you all know that diamond and graphite are both made up of carbon? How much of you all did not know that? Diamond and graphite are both made up of only carbon. It's not made up of anything else. But which one is more expensive, diamond or graphite? Both of them made up of the same exact atom, carbon. Diamonds are obviously more expensive, right? Do you all know where you all can find graphite right now in your room? Where can you find graphite right now in your room? Your pencil tips. This is supposed to be a pencil. I think I did an okay drawing of a pencil there. The tip of your pencil, which is black, is made up of graphite. And graphite is made up of carbon atoms. However, when you take carbon and you link them up like this, you see this little pattern here? When you link them up like this, you get diamond, which is really expensive and really tough. And also, what's the color of diamond? It's clear. It just so happens, you see, when you take atoms and you connect them a certain way, it could possibly change a lot of things about the structure. It could change how tough it is. It could change the color. Graphite, however, when you arrange it like this in hexagons, when the atoms are arranged in hexagons, you get boring graphite, which is, well, it's black and it's not tough. Allotropes are different forms of the same element in the same physical state. It just basically means it's two different compounds, except the atoms are arranged differently. And because you arrange them differently, they have different properties. Which one of these here can conduct electricity? Can diamond conduct electricity? Or can graphite conduct electricity? Which one conducts electricity? Graphite, correct. Diamond does not conduct electricity, but graphite can conduct electricity. In fact, graphite is a really good conductor of electricity. Okay? Right, so I got two things. Unfortunately, you have all right. So let me tell you what we need to take down here. We need to take down what an allotrope is. Here's a slight explanation, a more in-depth explanation of the differences between diamond and graphite. How much of you all cannot draw diamond? Like graphite, easy to draw. I think if you all take your time, it's just hexagons, right? It's just hexagons. How much of you all are going to have trouble drawing the diamond structure? All right, so watch me draw the diamond structure. It's not real easy, but look at me. You don't have to draw the whole thing. All you have to do is start with one dot on top, and you have to be able to draw it for the exam from scratch. Yeah? Take one dot, go with me. Go down and draw one more dot. Right. Out of this dot, 3 arms are going to come out. 1, 2, 3. So from the second dot, draw 3 arms coming out. And at the end of each arm, put a dot. All right. I'm going to draw the next one in a different color. Right? What's going to happen? Oh, that's a terrible color. All right. Out of each one of these here, the 1, 2, 3, one arm is going to come out, and out of one arm, right, 3 arms come out again. So each arm is going to sprout 3 arms. You know, it's kind of hard to see, but you have to practice drawing it in the exam. Right, so each arm sprouts another 3 arms, and you'll be good up to there in the exam, right? You don't have to go further than that. So I hope the different colors will make it easier to, you know, to recognize. You get a little 2 marks for drawing that in the exam. This is the structure of what? Diamond. Graphite, easy to draw, right? You're just drawing hexagons next to each other, right? You'll be good enough. It shouldn't be too hard. You draw one on top, one underneath, and you draw some dashed lines in between them, and you're good to go. Let me know when you're finished with everything on the screen. Right? So allotropes are basically made up of the same exact elements, except the atoms are arranged differently. No, for diamond, you only have to draw up to here for the exam. You see how I just draw the black and the 3 colors? You don't have to go down more. This is more than enough to give you full marks in the exam. I guarantee you, that is more than enough. Someone asks a question, right? These lines here, right? In real life, right? Like if you were to zoom into a diamond structure, or you use a real powerful microscope to see graphite, this is not a real line. You will not see a line, like a physical link between the carbon atoms. These here are what you call bonds. It's like a unseeable, like unseeable. They invented a word for that. It's an invisible force between the atoms holding them together. You call it bonds. And there are many different types of bonds, right? It have, which we will discuss just now. It have ionic bonds, covalent bonds. It have metallic bonds, and then the most important bonds, James bonds. That's a joke. That's a joke. Right. Don't burn down my house. Just came up with that on the spot. All right. So some of y'all are probably wondering what kind of bonds it have in between this. Are the bonds in between the carbon for diamond? Is it ionic bonds? Is it covalent bonds? Is it metallic bonds? There will be a way to figure out what kind of bonds or invisible forces it have in between different types of atoms. Okay. All right, about 3 or 4 people are finished. All right, so a little cut scene here, guys. So you finally make your way out of the woods. Oh, and unfortunately, you made it to this swamp-like area. Doesn't look too pleasant. And you have this huge toad here, this frog here. All right. Here's what. If you guess the number between 1 and I need for everyone to guess a number between 1 and 20, 1 and 20 included. And if you guess the correct number, you will be rewarded with something. The toad, the magical toad, will give you something. Send it on the chat, guys. Send it on the chat. Any number between 1 and 20. 1 and 20 can be included. Let's see if you guys get lucky. Today is what, Friday? Friday, what, 15th? If you're feeling lucky with 15, choose 15. I honestly don't know the number. I made this a long time ago. All right, guys, so let's see who You only one number you can choose, guys. You can't choose two numbers. Only one number. All right, so let's see. Let's see if you got lucky. Did anybody choose 5, 11, or 19 and send it on the chat? 5, 11, or 19? If you guessed one of these numbers, this is what you win. Once you guessed any of these numbers, add 5 to your strength and add 4 to your magic. Right? So congratulations to the winners who guessed luckily. Add 5 to the strength, add 4 to the magic. Yeah, it just feels good when you guess it correct because it's 3 out of 20. All right, let's move on. Let's talk about happy and sad atoms. This is going to be an interesting talk over here. This is how I like to start my explanations on how reactions happen. Sodium, for those who know, okay, let's take potassium, right? Potassium from your periodic table, right? Potassium is a metal, and potassium is in group 1. Anybody could tell me what happens when you take potassium and you put it in water? Anybody could tell me what happens when you mix potassium and water? I'm sure your teacher has warned you about this already. In fact, in the lab, you are not allowed to even touch potassium because whenever potassium touches water, it explodes. There's an explosive reaction. Okay, so I guess you could probably imagine that. You could probably imagine potassium falling in water. It have this big explosion and people get blown across the classrooms. All right. So that's an exciting example of what a reaction is, right? An explosion is what? A reaction. What about, let's talk about a more boring type of reaction. Iron. What happens when you now buy it from the hardware? It's a nice grayish, silveryish color, right? What happens when you leave iron out in the open for too long? It begins to do what? It starts with the letter R. It begins to rust. And rust has a kind of brownish, reddish color. I think everybody has seen rusty iron. Did you all know rusting is also a type of reaction? Like when you leave iron to rust, that is a type of reaction. It's just what? Not an exciting reaction like potassium falling in water where you get this Hollywood explosion. How much of you all have ever wondered what a reaction is? Have you ever thought about what a reaction is? Be honest. Like in terms of an atom, what are the atoms doing in a reaction? That is what we're going to talk about now. And it has all to do with happy and sad atoms. Okay? In reactions, electrons either leave an atom or they come and join an atom. So in other words, it's like this. If I have one atom here and another atom here, right? I'm not drawing the shells and things, right? I just saying the dots represent atoms. During a reaction, electrons either leave, so you have electrons with a negative charge. Electrons either leave the atom or electrons either join the atom. That is all I shouldn't say, well, that is all a reaction, isn't it? Electrons leaving an atom or joining an atom. But there are certain rules to whether electrons should leave an atom or whether it should gain atoms. Look at this scenario here, right? It doesn't matter what the atom is, okay? How much electrons does it have right now? Count up how much electrons it have in total in the first atom. I'll help you do a count here too. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 electrons, right? I don't care about neutrons today. Tell me, how much protons is it supposed to have? But let's ask you, how much protons is it normally supposed to have? 11. For this to be a neutral atom, it's supposed to have 11 protons. It's supposed to have 11 protons, and, well, we know it has 11 electrons. We counted it up. For atoms to be happy, being neutral has nothing to do with happiness. I want to get that out of the way one time. A lot of people will say this atom is happy because it has 11 protons and 11 neutrons, so they cancel out. That has nothing to do with happiness. Happiness has to do whether its outer shell is filled. Remember, the first shell can hold 2, and all the other shells can hold up to how much electrons? 8. Always look at the last shell to figure out if an atom is happy or not. Is the first atom happy? Keep in mind, for it to be happy, its outer shell must be filled. Is it happy or sad? It is sad because its outer shell can hold 8, and it only has how much? 1. So he is definitely what? Sad. Okay? To become happy, its outer shell or its last shell has to be filled. Now, there are 2 ways it can accomplish happiness. And you all are going to tell me which one is easier. How much more electrons does it need to be happy? How much more electrons? 7 more, right? So it can say, all right, to be happy, I'm going to work at it. I'm going to gain how much? 1, 2, 3, 4, 5, 6, 7. Now, if it were to gain 7 more electrons to make it 8 in total, because it had 1 to start with, then it would be happy. So that's one way it could accomplish happiness. Or what could it do? Instead of gaining 7, and it could just say, hey, get lost. The one on the last shell here. And the atom could say, hey, get lost. And he could what? Leave? Because if he leaves, right, then there will be no third shell. The last shell would be the second shell. Which one is easier in this particular case? To gain 7 or just to say, hey, the last electron, take a hike, get lost. Right. Electrons will always look for the easier way to accomplish happiness. Losing 7 is harder. Sorry, gaining 7 is harder. Losing 1 is easier. And that is what a reaction is all about. Whenever an atom is unhappy, it's going to try to achieve happiness by either gaining electrons or losing electrons. And it's because of this gaining or losing electrons, you just get a reaction. You see, when atoms lose electrons or gain electrons, it is have a physical effect, like an explosion, or a boring effect, like rusting. All right? But to lose or gain electrons, it is have to enter something called bonding. And when atoms begin to bond, when I begin to use that word, Bonding really means the atoms is doing something with the electrons, either losing or gaining electrons, and it's called a reaction. How about the second atom? Look at the second atom. Is this atom happy right now? Is he happy? Right now, he has 1, 2, 3, 4, 5, 6, 7, 8, 9. It has, so it should have 9 what? Protons, right? Right. It's not happy, right? Because its outer shell only has 1, 2, 3, 4, 5, 6, 7. Remember, that shell could hold up to what? 8. For him to accomplish happiness, is it easier to lose 7? Because he could either lose 7 and revert back to the first shell, or he could do what? Which one easier, to lose 7 or to gain 1? Right, isn't it easier for him just to gain 1 electron? Think about it. The atom is going to look for the easiest way to accomplish happiness. Look at the third one. What do you think he is going to do? His outer shell has how much? 1, 2, 3, 4. Remember, the outer shell could hold 8. So if he enters a reaction, what do you think he will do to achieve happiness? You notice this one is a kind of funny one, because he could either gain 4 or lose 4. Think about it. If he gain 4, it will have 8. But if he lose 4, he will revert back to the first shell. Either way, he's going to be happy. It's not easier. In this case here, it doesn't matter which one it does. So whenever atoms have 4 outer electrons, it could go either way. It could either gain 4 electrons or lose 4 electrons to accomplish happiness. Anybody could give me an example of an atom that has 4 outer electrons? We just discussed it a few minutes ago. It starts with the letter C. Carbon. And because carbon can go either way, it can lose or gain to achieve happiness. Carbon is very, very, very important in chemistry. That concept of being able to go both ways to achieve happiness is super important. And you'll see why later on, right? No problem, Jada. Right? So this one here, I drew it by mistake. How about this one here? What does he need to do to achieve happiness? Does he need to gain 4 electrons? Sorry, does he need to gain electrons or lose electrons? The last one in the corner here. Hi, Giovanna, right? You all realize he already happy, right? He already happy. Doesn't he have 8 electrons on his last shell? So he already happy. So do you think he will anytime soon be entering a reaction? Think about it. Atoms only enter reactions to achieve happiness. An atom will enter a reaction so it can either gain or lose electrons to become happy. Whenever, right, atoms have its last shell completely filled, he will never enter a reaction. Why would he enter a reaction? He's already happy. So anytime you have atoms who are happy, you usually classify those atoms as unreactive. They are not reactive. Don't expect anything cool from them. They will not explode. It will not cause rusting. They just sit there for their entire lives, always being happy, not mingling with anybody. They're just happy. Anybody can tell me which group, that's the vertical ones, which groups will be unreactive? Which group is always happy? Group 8, correct. Remember group 8, the noble gases? That's like helium, neon, and all of them. You call those the noble gases. They are very unreactive because they are the happy atoms. Right? Great. Right, so I'm not too sure how much I have. Oh, just one thing I wanted to say. Whenever, I know I said it already, right? But whenever atoms lose electrons, they become more positive. When atoms gain electrons, because electrons are negative, they become more negative. Okay? All right. So I don't think it have too much here you don't have to take down anything here, but you think everyone could memorize this concept here? It's going to be a real important concept right throughout chemistry. You think you understand the concept? For an atom to be happy, it either gains electrons or loses the electrons, so its last shell is filled, but it will look for the easiest way to do so. Great. So let's move on here. Right. All right. So let's talk about ionic bonding. I need some help here with these diagrams here. We have something called sodium and we have something called fluorine. Sodium is not happy because if you look at sodium, if you were to draw sodium, it would have 1 electron on its last shell. Fluorine, if you were to draw it up, it would have 7 electrons on its last shell. So everyone agrees that both atoms right now are unhappy. Everyone can agree with that, right? Sodium is supposed to have how much protons to balance off the 11 here? It's supposed to have 11 protons. I don't care about the neutrons right now. Fluorine has how much electrons? 1, 2, 3, 4, 5, 6, 7, 8, 9. It has 9 protons to balance off the 9 electrons. Notice something, and this is going to be very important for CSEC. If you have 2 different atoms at the same time on a piece of paper, for one atom, you have to use circles for the electrons. And for the other atom, you have to use X's. You have to. You can't use circles for both diagrams or X's for both diagrams. You have to choose different symbols to represent the electrons. Are these 2 a good match for each other? What do you think? Both of them are unhappy. But even though both of them are unhappy, each of them realized, wait now, if 2 of us come together, you have something I need and you have something I need. Let's see what happens here, right? Keep your eye on this guy over here. The 2 are going to come together. So this electron is going to disappear. You see, disappear there. And guess who he's going to give it to? He's going to give it to the fluorine. Did you all see that? He gave away his electron to the fluorine because the sodium doesn't want that electron, but who actually wants it to be happy? The fluorine. What's going to happen to this 3rd shell here? Anybody can tell me? Do we need this 3rd shell now, knowing that it has no electrons? Let's go back. Let's go back. Some people missed it. All right. Right. Look at this here, guys. So I know my mouth getting a little tired. Keep your eye on this electron here. Remember, for sodium to be happy, he needs to get rid of this 1 electron because it's easier to get rid of 1 rather than gain 7. He's going to take this electron and give it to who? Fluorine, because fluorine just needs 1 more to be happy. He's going to disappear, reappear. Do we need this 3rd shell? Sorry to ask back the question. Do we need this 3rd shell on the sodium now? The answer is no, because that shell has no electrons. What is his purpose? He will fade away. So look at the diagram properly. He's going to fade away now. See, he fade away. Is everybody happy now? Is sodium happy and is fluorine happy? Both of them are what? Happy now, okay? Because both of them, their outside shells are filled, right? So I changed it to happiness there. But something happened now. What is the overall charge on the sodium? Remember, nothing happened with the protons. It had 11 protons, but now it have how much electrons? It doesn't have 11 anymore. It only has how much? 10. So what's the overall charge of sodium now? And it have more positive than negative. So what's the overall charge of this atom now? Positive. And what's the overall charge on the fluorine? Remember, the fluorine had 9 protons, but now it have how much? 10 electrons. It have more negative than positive. So his overall charge is negative now. Not just negative, but -1, and this one is +1. So you see, by losing and gaining electrons, the atoms achieved happiness, but now they have overall charges. Which one is the cation? Remember, ions are atoms that have an overall charge now. Which one is the cation? Any sodium is the cation because it has an overall positive charge. And the fluorine, because it has an overall negative charge, is the anion. Remember, anions have a negative charge and cations have a positive charge. What do you know about positive and negative? And opposite charges attract, because they had an agreement about exchanging electrons. They are now charged. The positive will be attracted to the negative. So the sodium is locked with the fluorine now because the opposite charges attract. Both of them lock into each other. You call this type of bonding ionic bonding, but it only happens between metals and non-metals. Sodium is a metal and fluorine is a non-metal, right? And this is a type, you call this a reaction because electrons are involved. Electrons are going from one atom to the next atom. And because there's a transfer of atoms, charges develop. You get a cation and an anion, and opposite charges attract. So these two are stuck with each other for the rest of their lives now. It's like a marriage. All right. Take down everything on the screen here. Right? Well, at least the final diagrams here, right? Note, oh, by the way, the reason why we use different symbols for the electrons. You all notice if somebody now comes to class, do you realize that you have a circle here? They would know that this electron, because it is a circle, it came from this atom. So that is why you use different symbols. Okay? So you know, even at the end of the question, where the electrons first originated from. Right, so someone has a question and I have to research it, right? Someone said that non-metals should be represented by dots and the metals should be represented by X's. To be honest, I've never heard about that, but sometimes I learn new things, but I will do some research on it. As far as I know, you're just supposed to choose one to be the circle and one to be the X, irrelevant of whether it's a metal or a non-metal, but I will do some research because sometimes I am wrong.